Welcome to the Solutions to the Regents Physics Modern Physics problem set, problems numbers 9 through 13. Number 9, compare the de Broglie wavelength of a baseball moving 40 meters per second, which is about 90 miles per hour, with the size of the baseball. If you don't know the size of baseball, I went ahead and measured it. It's about 7 centimeters in the metric system. So they want us to compare the wavelength produced by the baseball moving to its size. Well, in order to do that, the de Broglie wavelength equation is lambda equals h over p, and p is its momentum, which is mass times velocity. I went ahead and put a baseball on a balance and massed it, and found that the baseball had a mass of 145 grams, which of course is 0.145 kilograms. Remember that when doing the de Broglie wavelength calculation, you have to use the joule-second form of Planck's constant. And of course there we have the 40 meters per second in standard velocity form. We go ahead and we do the calculation. We get 1.1 times 10 to the negative 34 meters. So compared to 7 times 10 to the negative 2 meters, this wavelength is much, much, much smaller. It's not even detectable on the electromagnetic wave spectrum. Number 10. What is the momentum of a photon of yellow light whose wavelength is 600 nanometers? Okay, so this switches things around yet. Here we're looking at momentum, so P equals h over lambda. Again, make sure you use the joule-second form of Planck's constant. And the wavelength was given as 600 nanometers, so 600 times 10 to the negative 9, the metric prefix nano. We go ahead and we divide, and we should get 1.1 times 10 to the negative 27 kilogram meters per second on that unit of momentum. Number 11, find the de Broglie wavelength of a deuteron of mass 3.3 times 10 to the negative 27 kilograms. They give you the m value. That moves with a speed of 2.5 times 10 to the fourth meters per second. They give you the v value. And is this wavelength detectable? Well, we have lambda equals h over mv, joule-second form of Planck's constant, divided by its mass times its velocity. We go ahead and we calculate, and we should get 8 times 10 to the negative 12 meters. You then go ahead and look up on your reference table, and you discover, yes, that it's detectable. 10 to the negative 12 on wavelength is in the X-ray and overlapped on the gamma ray spectrum. Number 12, an electron is accelerated across a potential difference of 54 volts. Find the maximum velocity of the electron and calculate its de Broglie wavelength. Determine whether or not it's detectable. They told us it's an electron, so we know it's charged. They told us the potential difference, 54 volts, so they gave us V. What's the tie-in between the information they gave us and finding the maximum velocity? It's that the maximum kinetic energy is equal to V times Q. This is a conservation of energy, really, because the maximum kinetic energy is equal to the electric potential energy, which is stored from the work done to accelerate the electron. And the work done would be V times Q. So either way you look at it, either conservation energy or work energy theorem, you end up with the same result here. So V times Q equals the equation for kinetic energy, 1/2 mv squared. We go ahead and we substitute. We have mass of an electron. We have our voltage of 54 volts, and we have the charge of an electron, mass and charge, all off the reference table. We go ahead and solve for the velocity. Don't forget to take the square root of all your math when you're ready to solve for the velocity here. Now you should get 4.4 times 10 to the 6 meters per second. Now that we know the speed, we can go ahead and calculate its wavelength. So de Broglie wavelength is h over mv. Planck's Planck's constant in joule seconds, mass 9.11 times 10 to the negative 31 kilograms, speed 4.4 times 10 to the 6 meters per second. And when you do the math, you should get 1.7 times 10 to the negative 10 meters. And of course, this, when you look it up on the electromagnetic spectrum, is detectable. All right, our last question for homework today, 13. A neutron is held in a trap with a kinetic energy of only 0.025 electron volts. Is there such a thing? Yes, there's such a thing as a neutron trap. So they give you the kinetic energy and they tell you that it's a neutron. They want to know the velocity of the neutron, and they want you to calculate the de Broglie wavelength and whether or not it's detectable. Well, the velocity is going to come from Ke equals 1/2 mv squared. The problem that we have here is that our kinetic energy is given in electron volts, and you need to have it in joules in order to use this equation. So we go ahead and we convert that 0.025 electron volts to joules using the conversion given on your reference table, and then set that equal to 1/2 mass of neutron given on the reference table times v squared. We go ahead and we solve for v, and we should get 2.2 times 10 to the 3rd meters per second. Now that we know its velocity, we can go ahead and calculate its wavelength using the de Broglie wavelength equation. Lambda equals h over mv. Planck's constant in joule seconds. There's our mass again off the reference table, and our answer from A, 2.2 times 10 to the 3. We go ahead and do the math, and we should get a wavelength 1.8 times 10 to the negative 10 meters. And yes, it's detectable. All right, that'll do it on our problems for homework on 9 through 13. More to come on this quantum theory evidence problems that you've been doing here as we do number 14 together in class tomorrow.